Hello and welcome to this video. This video will be about attractors in 1D systems, and we will talk about the role they play in spike dynamics. But before we can talk about attractors, we have to recap dynamical systems. Since functioning neurons are dynamic, so they change their membrane potential and firing rates over time, a model is needed which is mathematically based on such dynamic systems. Such dynamical systems are mathematical models that can describe time-dependent processes. They are described by differential equations. In our case, we are talking about 1D systems, dynamical systems that are described by only one single differential equation. And since differential equations always denote a relationship between a function v and its derivative, our system needs to contain such a v. V is a scalar-dependent variable denoting the current state of the system that we want to model. To actually model the system, we also need its derivative with respect to the time t. This can be expressed as a function f of v, where f denotes the relationship between v and its derivative. So f of v determines the evolution of the system. We now have a dynamical system, and we can plot the graph of the function f, where the x-axis corresponds to the voltage. But what shall we do with this? Since we have a function that models the process of the time-dependent states in the system, one thing that we're interested in might be describing the behavior of our system, or in other words, towards which values does the system tend to evolve. For this, we have to find the rest points. Points where the variable v, so the state of the system, does not change. And this can only be the case for points where f of v, so the evolution of the system, is 0. Therefore, we are looking for the equilibria, the rest points. For a better visualization, let's have a look at the energy landscape. The zeros of f of v, either with a negative or positive slope, correspond to minima and maxima of E of v respectively. These are the only points where a ball, for example, does not move at all, as we can see here in the case of a fixed point with a negative slope. So for now we can conclude when v is exactly here, v would stay there forever. To go back to the question in the beginning, this is exactly what an attractor is. An equilibrium that attracts all nearby solutions, or in other terms, a set of numerical values toward which a system tends to evolve. However, we have to keep in mind that it is a certain sort of equilibrium that we have just seen. For that, we have to look at its stability. The stability of an equilibrium is determined by the signs of the function around it. The equilibrium is stable when f of v changes the sign from plus to minus as v increases. Thus, it exhibits a negative slope. Obviously, for the system, all trajectories evolve towards the origin. Such an equilibrium attracts all nearby solutions, and it's called an attractor, here indicated by solid circles. For picturing purposes, it can be seen as the center-bottom position of a damped pendulum, the level and flat waterline of sloshing water in a glass, or the bottom center of a bowl containing a rolling marble like we have here. A stable equilibrium point is the only type of attractor that can exist in one-dimensional continuous dynamical systems defined on a state line of real numbers. But of course, there are also other fixed points that we have gathered. I mean, if a one-dimensional system has two stable equilibrium points where the sign changes from plus to minus, then they must be separated by another fixed point, which cannot be stable because the sign has to change back from minus to plus. What of them? Well, as you can see, they exhibit a positive slope which renders the equilibrium unstable. The system moves away from the origin in both directions, therefore the origin, in this case, is an unstable fixed point or repeller, indicated by an open circle in the phase space plot. For example, in the case of a marble on top of a hill, that point at the top of the hill is a fixed point, but not an attractor, but a so-called repeller. Or if we go back to the example of the pendulum, then once it has been moved from the unstable position, it will never be able to return to it again. So a sufficient condition for an equilibrium to be stable is that the derivative of the function f with respect to v is negative at the equilibrium, provided that the function is differentiable. And on the other hand, a positive slope implies instability. So to summarize what we have said so far, the principal behavior can just be studied by the function f of v. First, the points where f of v is 0 need to be identified as fixed points, which can be either stable or not. Second, we look at the slope at that exact point to capture stability, and thus one can deduce whether an equilibrium is an attractor or not. With this method, we have two different ways to look at a differential equation. We could use either mathematical expressions and analyze the equation, or we could use the concept of fixed points. But now, what is so important about these equilibria, about the attractors and repellers? Well, especially the unstable equilibria are of great importance in spike dynamics, because they play the role of thresholds in one-dimensional bistable systems, so in systems with two attractors. They separate two attractor domains from each other, which can exhibit two very different behaviors. This modulation is thought to describe the essence of the mechanism of bistability in many neurons. Here, let's assume the state variable is initially at the stable equilibrium point state A, and that it can be kicked back and forth around the equilibrium by perturbations. Such small perturbations cannot kick it over the unstable equilibrium, so the state variable keeps moving towards the equilibrium point in A. Such a perturbation is called subthreshold. One speaks of superthreshold perturbations when they are large enough to push the state variable above the unstable equilibrium so that it is pulled towards state B. The unstable equilibrium acts like a threshold separating two states. The transition between two stable states, separated by a threshold, is relevant to the mechanism of excitability and action potential generation of many neurons. On the basis of the action potential, whose sequence is well known, the process can be vividly explained. So, if we go further with the action potential case, when neurons get input and thus remain excitatory, it moves the neuron to the right, making the membrane potential more positive, or inhibitory to the left, making it more negative. There occur small fluctuations. The membrane potential will always come back to the starting point because after some time the sphere has sort of balanced out and is back to the original equilibrium. As long as the system remains in this area, it will always return to the rest state, whatever will happen. So small perturbations leave the state variable in the attraction region of the rest state. However, as soon as the perturbation, the input, is strong enough to go beyond the threshold of our unstable equilibria, then the situation changes. The system overcomes the threshold, makes a self-excitation until it gets to the state associated with this maximum voltage and would stay there. Thus, large perturbations initiate the regeneration process, the upstroke of an action potential, and the voltage variable is pulled into the excited state. The repolarization brings the membrane potential back to the resting potential, its starting point, but this is done by a different mechanism that is unimportant at this point. Thus we can say that the unstable equilibria separated two domains which have very different behavior. On the left, the concept of integration, and on the right side we would have self-amplification and the upward movement of spike production. And thus we hopefully achieved an understanding of a concept that can be arbitrarily complex. We don't necessarily have to understand the exact analytical solution to this differential equation, but we can still decompose the principal behavior of a differential equation into something that is integration and activation of a self-amplification. And we identified this based only on attractors, both stable and unstable. This simplification allows us to get qualitative insights into the dynamical system without having to analyze the whole mathematical expression. We hope you enjoyed watching this video. If you have any questions, don't hesitate to ask.